All right, welcome to The Explainer. Today, we're pulling back the curtain on the hidden computers that secretly run our world, embedded systems. And trust me, you probably bump into dozens, maybe even hundreds of them every single day, and you don't even know it.
Okay, I know what you're thinking. This sounds like the start of a really bad joke, right? A fighter jet and a digital camera. I mean, what could they possibly share? Well, the answer is actually way more fascinating than you might think.
Well, the big reveal is they're both run by a secret, dedicated computer. You see, your laptop can do a million things: browse the web, play games, do your taxes, the whole shebang. But these computers, nah, they're specialists. They're built from the ground up to do one thing, and do it perfectly.
And that, my friends, is an embedded system in a nutshell. It's a purpose-built little computer, a mix of hardware and software that's literally embedded inside a bigger device to do one specific job. The big thing to remember here is that it's not a jack of all trades, it's a master of one.
And seriously, once you know what you're looking for, you start seeing them absolutely everywhere. We're talking about the anti-lock brakes in your car, ECG monitors in hospitals, your smart TV, those robotic arms in factories, that F-35 fighter jet, and yep, even your microwave. They are the silent, invisible workhorses of our modern lives.
So how in the world do these things actually work? Well, the first big challenge they have to solve is translating between two totally different languages. The real world, the one we live in, is analog, kind of like the smooth, seamless way you turn an old-school volume knob. But computers, they live in a digital world. Everything is broken down into neat, tidy steps and numbers. So to get around this, embedded systems have this awesome little translator, the analog to digital converter, or ADC for short. Its entire job is to listen to a real-world signal, like a tiny change in voltage from a sensor, and turn it into a specific number that the system's digital brain can actually understand.
And here's a great example of just how precise this can be. Let's take something like an Arduino board, which tons of makers and hobbyists use. It has a 10-bit ADC. What that means is it can chop up a 5-volt signal into 1,024 distinct levels, from 0 to 123. So a tiny little change in voltage gets reported as a different number. It's that simple and that precise.
Okay, so who's actually doing all the thinking here? Well, that would be the microcontroller. It's basically a brain on a chip. It's a whole computer, processor, memory, I/O ports, all crammed onto one tiny little piece of silicon. It's the command center for the whole operation.
So let's walk through it. Picture this. The microcontroller gets a number from the ADC. The software on that chip has a really simple set of instructions, right? Something like, hey, if that number creeps past 512, kick on the cooling fan. Boom. Simple, logical decision. But okay, that brings up a really interesting puzzle. Turning something all the way on or all the way off, that's easy for a digital brain. But what about something in between? How can this digital brain, which only gets on or off, do something smooth and gradual, like dimming a light?
Well, the answer is this super clever trick called pulse width modulation, or PWM for short. It's this amazing technique that lets a totally digital system basically fake a smooth analog signal. It's pretty brilliant, actually.
Think about it like this. Imagine you could flick a light switch on and off, like thousands of times a second, so fast that your eyes can't even keep up. You wouldn't see flickering. You just see a light that looks like it's continuously dimmed. That's PWM in a nutshell.
And that's where this key idea of duty cycle comes in. It's just the percentage of time that the switch is in the on position. So if the switch is only on for, say, 25% of the time, that's a low duty cycle. The LED gets less power, so it's dim. Crank it up to 75% on time and you get a higher duty cycle, more power, and a brighter light. It's controlling an analog world just by playing with time. And you know what's crazy? How simple this is for a programmer to actually do. In the Arduino world, for example, you literally just use one command, analog write. You feed it a number, say from 0 for totally off to 255 for full blast, and the chip does all that crazy fast flicking for you. It's awesome. Okay, so we've got it. These systems can sense the real world and then do something about it. But think about how complex modern stuff is. A car has to manage its engine, its brakes, its entertainment system, and its airbags, all at the same time. And for some of that stuff, timing isn't just important, it's everything. It's literally the difference between life and death. So how on earth does a system juggle all of that without dropping the ball? Well, that's the job of a real-time operating system, or an RTOS. It's a special kind of OS that doesn't just manage tasks, it guarantees that they get done within a very strict, predictable time frame. Seriously, think of it like an air traffic controller for your software. Its one and only job is to make sure every single task lands on time, every time, with no exceptions.
But here's the thing. Not all real-time tasks are created equal. You've got your hard RTOs. This is for things like a car's airbag. If that system is even a millisecond late, it's a catastrophic failure. Period. There's zero room for error. Then you have a soft RTOs. That's more like streaming a video. If it misses a deadline, you might get a little stutter or a buffering wheel for a second. It's annoying, sure, but the whole system doesn't collapse.
So when you pull it all together, what do you get? The crucial point is that these hidden systems aren't just about convenience anymore. They're what make our world safe, efficient, and smart, all by totally mastering the dimension of time. And that, of course, leaves us with one big final question. As we barrel towards this future of self-driving cars, smart cities, and the Internet of Things, the pressure on these little hidden brains is going to be absolutely immense. So the question really isn't if they'll be important. The real question is, how are they possibly going to evolve to handle the mind-boggling, real-time chaos of the world we're building right now?